Hi there, and welcome to the live stream here at o'kellychemistry.com. I'm Ivana O'Kelly, and thanks for joining me this evening. In this live stream, we're going to cover electromagnetic radiation, duality of light, and finally, we'll finish up with some energy calculations. So make sure you have a pen and paper and a calculator at hand. If you have any questions during the live stream, I encourage you to go ahead and enter them into the chat. Ladies and gents, let's get started. So here's our agenda. So we'll start off with electromagnetic radiation. So what is electromagnetic radiation? So it's energy that takes many forms and it travels in waves. Now the only part of the electromagnetic radiation that humans can detect is visible light. So as chemists, we want to see how this relates to matter. So in an atom, electromagnetic radiation is created when an electron is accelerated by an electrical field causing it to move. And this movement produces oscillating, so that's moving, electric and magnetic fields, and they are traveling at right angles to one another. And they do this in a bundle of light that we call a photon. So here is a classic wave, and we're going to look at this in terms of electricity and magnetism. So I'm going to underline electromagnetic here. So starting off, we see that the top of the wave is what we call the crest. And the bottom of the wave is what we call the trough. The distance from the crest of one wave to another, we refer to that as wavelength. So let's write this down here, wavelength. And that's represented using the Greek letter lambda. Now this wave is traveling in this direction. So this is the direction that this wave is traveling in. So in terms of the electric field, it is traveling in this direction. So this is our electric field. Our magnetic field, we said, is traveling at right angles. So I'm going to go ahead and draw that in here for us. And we see this way and this way. So this represents our electric field. So it's traveling at right angles. So this would represent our magnetic field. So what are the different parts of the electromagnetic spectrum? Well, there are 7 different parts, and the first one we're going to look at is our radio wave. So this represents a radio, and our radio waves have the longest wavelength. Next to a radio wave is our microwave. Followed, this is a remote control that uses infrared. So I'm just going to write down IR for infrared. Followed by our visible spectrum, which we said is the only part of the electromagnetic spectrum that we can see. This represents our ultraviolet. So this is UV light. And again, the wavelength is decreasing as we're moving down through our magnetic spectrum. This represents an X-ray. And lastly, our wavelength, our type of radiation that has the shortest wavelength is our gamma rays. So electromagnetic radiation, what are they? They're streams of massless particles called photons, and they're traveling in wave-like patterns, and they all travel at the same speed. So the speed that they travel at is the speed of light. And our speed of light is equal to 3.00 times 10 to the 8 meters per second in a vacuum. So in terms of wavelength, so think back to that diagram that we just labeled. Wavelength, as we move in this direction on this electromagnetic spectrum, going from radio waves all the way down to gamma waves, our wavelength is going to decrease. In terms of frequency, So that our frequency is the number of waves that pass a particular point in 1 second, and our frequency is going to increase. So remember that these have an inverse relationship to one another. So looking at the visible spectrum, here are the specific wavelengths of each of the colors of our visible spectrum. So if we take white light, we know that it's made up of our Roy G. Biv. So I have 3 examples that I'd like you to try. So can you identify these colors based on their specific wavelength? So look here on the left-hand side and see if you can tell me what are these colors. Give you a moment. Okay, so for the first one here we have 452, so that's falling between our blue category. So that would represent blue light. So blue light has a wavelength between 440 and 490 nanometers. The next one, 415, so that's going to fall in our violet range. And our last one, 623, is going to fall under our red wavelength. So in our calculations, we'll have to determine different wavelengths, and based on the wavelength, we can determine what color of light is actually emitted. So I mentioned there the relationship between wavelength and frequency. So I've listed out all of the different parts of our electromagnetic spectrum. So looking at the wavelength as we go down here, what are we seeing? The trend that we see here is that the wavelength is increasing. So going from gamma rays to radio waves, our wavelength is increasing. And this is the opposite to how it was on the first diagram that I showed you. And again, that's important because depending on your reference table, they can be written in either direction. So what we see about frequency, as we go down here, our frequency is decreasing. So that's what we refer to as an inverse relationship. So when something is increasing, the opposite, the decreasing, is happening to the other variable. So it's important that you realize that wavelength and frequency have an inverse relationship. So if we have a long wavelength, so our longest wavelength that we have on our electromagnetic spectrum is our radio wave, the frequency will be low, and that will result in a low energy. For short, our shortest wavelength is gamma. It's going to have a high frequency, and as a result of that, the energy is also going to be high. So the inverse relationship is between wavelength and frequency, and our frequency and energy are going to be the same. Okay, so moving on to, is light a wave, or is it a particle, or is it both? So in terms of a wave, light is going to pass through space, air, or water, and it's acting like a wave. And there was an experiment that was carried out called the double slit experiment, and they created a wall that had a double slit in it, and they shone a light at the double slit. So this is their light source, and they predicted that when the light source passed through the double slit, that they predicted that there should be 2 bright spots on the back wall. But in essence, what actually happened was they noticed that there was an interference pattern on the actual back wall. So that refers to our light traveling as a wave. So c represents the speed of light, and it's equal to the product of our wavelength times our frequency. Now, in terms of a particle with light, light is interacting with matter when we're talking about it being a particle. And Max Planck conducted an experiment called the black body radiation, and he observed that matter can either be absorbed or released in energy in whole number intervals. So this gave rise to a quantum. And the intensity of the light is emitted as a function of the temperature. So what he concluded was that for each temperature, there is a maximum intensity of radiation that is emitted by a black body object. So as a result, the intensity is not following a smooth curve as the temperature increases. And then Einstein, he had a very famous experiment which he received a Nobel Peace Prize for, called the photoelectric effect. And what he discovered was that the electric current can be generated if light of a certain frequency, regardless of its intensity, if it hits the surface of a metal object, it's going to release it as a photon. So in terms of light being a particle, we have this formula where the energy is equal to Planck's constant times its frequency. So now we're going to look at some important variables and units. So our first one is our speed of light. So our speed of light is represented by a lowercase c, and it's equal to 3.00 times 10 to the 8 meters per second. Now in physics they'll generally go with 2.998, but in chemistry we tend to round it up to 3.00. Our wavelength is measured in meters, and the variable is our Greek letter called lambda. And with wavelength we have to remember that if we have nanometers and we want to convert it into meters, we know that 1 meter is equal to 1.0 times 10 to the 9th nanometer. In terms of frequency, that will be measured in hertz, which is the symbol Hz, or it can be cycles per second. For energy, energy will be measured in joules with a capital J, and our Planck's constant is going to be 6.626 times 10 to the negative 34 joules times seconds. And here are some of our formulas that we're going to use. So C is equal to our wavelength times our frequency. So our frequency, putting this here on our list, is using the Greek letter nu. So it's like an italicized V. And our second formula will be our energy is equal to our Planck's constant times our nu, which is our velocity. Now we can also combine both of these together, and algebraically we'll come up with energy is equal to Planck's constant times the speed of light divided by the wavelength. So let's go ahead and try an example. So the question reads, what is the wavelength, so that's going to be our unknown, of a wave that has a frequency of 3.76 times 10 to the 14 hertz. So the formula that we're going to use is our speed of light is equal to our wavelength times our velocity. So we are looking for the wavelength, so we're going to make that the subject of our formula. So wavelength is equal to c divided by our v. So remember that our c is a constant, so it's 3.00 times 10 to the 8 meters per second divided by our frequency, which is 3.76 times 10 to the 14. And we're going to use s raised to the minus 1 so we can cancel out our units. So let's go ahead and cancel out our units. So our seconds are going to cancel, and that's going to leave us with meters. So let's go ahead and turn on our calculator. And we're enter in 3.00 E8, and we're going to divide that by 3.76 E14, and we see that we have 7.978. So looking at our significant figures in our question, we have to have 3 sig figs, so that will be 7.98 times 10 to the negative 7. So 7.98 times 10 to the negative 7 meters. Now, if you were asked to convert this into nanometers, so make sure that you would take your meters. So you take your 7.98 times 10 to the negative 7 meters, and you would convert that into nanometers. And 1 meter, because again you're always placing your 1 beside the larger value, is equal to 1.0 times 10 to the 9th power. So if we go ahead and multiply our answer by 1.0 EE9, we see that we get 797.87. So 797.87 nanometers. But remember, our final answer, we have to take into account our number of significant digits. So we can only have 3. So that will be 798 nanometers, which falls under the ultraviolet category. So next question, what is the frequency of 6.9 times 10 to the negative 13 meters? So again, we're using our same formula. So C is equal to our wavelength times our frequency. So we're looking for our frequency. So our formula will be C divided by our wavelength. So again, our C is 3.00 times 10 to the 8 meters per second. And we're dividing it by our wavelength of 6.90 times 10 to the negative 13 meters. In terms of our units cancelling, our meters will cancel out, giving us our frequency of hertz. So let's grab the calculator and we'll type in 3.00 E8 and we will divide that by 6.90 EE negative. Again, don't press the minus sign. And that gives us 4.347. And again, we want 3 sig figs, so it'll be 4.35. So final answer will be 4.35 times 10. And our exponent has a value of 20. And it will be frequency, which will be hertz. Or you can write S minus 1. So check with the teacher which one they want you to use. So what we did was we determined which formula we needed. We rearranged our variables. So we made frequency the subject, and it was C divided by wavelength. We wrote down our numbers, we cancelled our units, we put them into the calculator, and we got our final answer, making sure that we followed the correct number of significant digits. Okay, so here's another question, and it reads, what is the frequency of a photon of energy that has a wavelength of 445 nanometers? So this is an example of where we have to take our nanometers and we're going to have to convert it into meters. And once we have it converted into meters, we'll solve for V. So let's go ahead and convert our 445 nanometers into meters. So 1 meter is equal to 1.0 times 10 to the 9th. And once we get that value, we're going to divide that into our C. So we're looking for V, which is equal to C divided by our wavelength. So let's go ahead and write down our 3.00, our speed of light. Grab our calculator. So we have 445, 445, and we are dividing by 1.0 E9, giving us 4.45 raised to the negative 7. So 4.45 times 10 to the negative 7, and that will be meters. So now we're going to take our 3.00 EE8 and we'll divide it by, we can just go up here, and we see that we get 6.74 times 10 to the 14th. And our unit, we're looking for frequency, is going to be hertz, or s to the minus 1. So again, paying attention to your units is extremely important in these energy calculations. We saw our nanometers, we had to convert it to meters first of all, and once we had that done, we divided it into our speed of light, making sure we cancelled our units, so our meters cancelled, leaving us with our hertz. So let's see if we can figure out what is the colour of this light. So based on the 445, if we go down here and we look at our wavelengths of light, what colour do we see? We see that it falls within here. And it's ironic we're using a green pen, but it is blue. Blue written with a green pen, huh? Okay, next one. Here's actually one that I'd like you to try. So the question reads, what is the wavelength of a 109.6 megahertz wave? Now what I will tell you is you have megahertz, so you have to make sure that your unit in this formula, your megahertz, have to be converted into hertz. So think back to your metric conversions. What's the relationship between mega and our base unit? So here I go. And we're looking for wavelength. So our wavelength is equal to c divided by our v. And our c we know is 3.00 times 10 to the 8 meters per second. And I have to make sure that my unit is hertz. So I'm going to take my 109.6 megahertz, converting that into hertz. We know that 1 megahertz is equal to 1.0 times 10 to the 6. So let's go ahead and grab our calculator. So 109.6, and we are multiplying it by 1.0 E6. And then we are going to take our 3.00 EE8 and we're going to divide it by that number. And we see that we get 2.737. So we should have, looking at our question, we need to have 4 significant digits. So we will put 2.737. So 2.737. And our wavelength, here it is in meters. So we're putting this answer in here. Okay, so next question, I want you to calculate the energy of a photon of energy that has a frequency of 2.5 times 10 to the 16th hertz. So the information we have is we have frequency and we want to calculate energy. So we'll be using Planck's constant in this question. So our formula is E is equal to HV. So our H, so E is equal to HV. Our H has a value of 6.626 times 10 to the negative 34, and our unit is joules times seconds. And we're multiplying it by the number in the question, which is 2.5 times 10 to the 16th hertz. So that's what our E is going to be equal to. So let's go ahead and enter that into our calculator. So 6.626 EE negative 34 multiplied by 2.5 EE16. And we see that we get 1.656. So looking at our question, we see that we have 2 sig figs. So we need to have 1.7 times 10 to the negative 17. And in terms of our units, our hertz are our s to the minus 1, so they're going to cancel, and that's going to leave us with joules. So again, how did I know that we needed to use this? I was asked to calculate the energy. So energy is E of a photon, and I was given the frequency. And then I multiplied my H by my V, and that was able to give me my energy in joules. All right, let's try another one. So in this question, it says, what is the energy, which is E, of an ultraviolet photon that has a wavelength of 1.1 times 10 to the negative 8 meters? So what is the relationship between energy and wavelength? Well, that is our combined formula. So what we'll do is we'll write down our Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. And we're going to multiply that by our speed of light times 10 to the 8 meters per second. And we will divide that by our wavelength, which was given in the question, 1.18 times 10 to the negative 8 meters. So energy is going to be joules. So before we do our calculation, let's go ahead and cancel out our units. So our meters are gone and our seconds are gone. So therefore we're left with joules. So putting all these values in the calculator. So open your parentheses, 6.626 EE negative 34 multiplied by 3.00 E8, and we want to divide that by 1.18 E negative 8. Press enter, and we see that we get 1.684 in terms of our final answer. Looking in our question, we see that we need to have 3 significant digits. So I would round that up to 1.69. So 1.69 times 10, and our exponent is negative 17. And our unit, because we're looking for energy, we saw by cancelling, we end up with joules. Not too bad. Okay, let's try one more. So this question reads, a photon of blue-green light has an energy of 4.40 times 10 to the negative 19 joules. So we know that this is equal to the energy, and it's asking us for what is the wavelength of this light, and our final answer needs to be in nanometers. So you guessed it, we're going to have to use our combined formula, but we're trying to solve for our wavelength. So how do we move that variable? We're going to have to multiply by wavelength on this side and wavelength on this side, so they'll cancel out. Make that look like a better lambda. So what will happen is then we'll divide by E, so our E will come down here. So our formula will be our wavelength is equal to our Planck's constant times our speed of light divided by our energy. So the top 2 values are constants. So let's go ahead and write down Planck's. So 6.626 times 10 to the negative 34 joules times seconds. And we'll multiply that by our speed of light, 3.00 times 10 to the 8 meters per second. And we will divide that by our 4.40 times 10 to the negative 19 joules. In terms of our units, let's go ahead and get those cancelled out of the way. So we're looking for wavelengths, so we know our final answer should be meters, and we see our joules, and our seconds are going to cancel out. So let's go ahead and put this into the calculator. Again, make sure you're using parentheses. So 6.626 EE negative 34 multiplied by 3.00 E8 and dividing that by 4.4 EE negative 19. Press enter and we see that we get 4.51, so 4.52 times 10 to the negative 7, and that is meters. But remember, in our question it asked us for our final answer in nanometers. So what we have to do now is we take this meter and we will convert that into nanometers. Again, place the 1 beside the larger value. So a meter is bigger than a nanometer. The relationship between the two is 1.0 times 10 to the 9th power. So let's put that into our calculator. So we have our answer and we want to multiply that by 1.0 EE9. Press enter and we see that we have 451. So we'll get 452. So our final answer is 452 nanometers. Okay, so let's review. We saw in this question we were given the energy, so that led us to believe that we would have to use Planck's constant, and we also had wavelength. So the relationship is we have to use our third formula where the two are combined together, and then our final answer needed to be in nanometers. So we converted from meters to nanometers. We made sure that we conserved our significant digits. So in the question, again, notice we're focusing on the decimal portion. That gives us 3 sig figs. So ladies and gents, here is a reminder that there are some energy calculations. So there's some energy calculations for you in the lesson here at OKellyChemistry.com. If you're watching this video, I hope you have good luck with this calculations. If not, and you're part of the live stream, we're going to hang out here, and if you have any questions, please feel free to ask them to me. And one last thing, don't forget, subscribe to OKellyChemistry.com. Ladies and gentlemen, see you next time.